For a function of two variables, the derivative of that function was the vector containing the partial derivatives. We will call the derivative either df, or more commonly we will use this upside down triangle called a nabla symbol. Eventually we will call this the gradient of the function f. In order for the derivative to exist at a given point, those partial derivatives fx and fy have to exist. So the key takeaway here is that the derivative of a function of two variables is a vector. And because it's a vector, we can then use vector properties to prove the following derivative properties. We can talk about linearity. If we have two functions f and g that are differentiable, so that means they are functions of two variables, and we are going to assume that the partial derivatives of each one of them exist. If we ever need to take the derivative of a sum or difference of those two functions, that means it's the same as taking the gradient of the sum or difference of those two functions. We can take a look at this in vector component form. What we are doing is taking this and whittling it down to a component-wise derivative. As such, we can split this up using properties of ordinary differentiation. We'll get fx plus or minus gx here, fy plus or minus gy here. Now, because of vector properties, we can split this up into the sum or difference of these two specific vectors. This is exactly the same as saying the gradient of f plus or minus the gradient of g, which is just the derivative of f plus or minus the derivative of g. Now, similarly, if you ever wanted to take the derivative of a multiple of a function, that's equivalent to saying the gradient of a function. And once again, we're just going to go back to the component-wise definition of what this means. We can use basic differentiation rules to remove the constant. That'll leave us with a partial derivative of each of the functions. Using vector properties, we know that we can take out a constant from any vector as long as it's in both entries. This gives us a constant times the gradient, a constant times the derivative of that function f. That's exactly analogous to the linearity rules that we learned about for single variable functions. There's also a product rule. If you ever need to take the derivative of a product of differentiable functions, that's the same as the gradient of this product of differentiable functions. As before, we go back to the component-wise definition, and you can see that everything boils down to just using basic rules that we've encountered before. So in each component here, we're going to have a product rule. So we'll have fxg plus fgx in the first component, fyg plus fgy in the second component. We can split this up into two separate vectors. We'll have fxg in the first component, fyg plus fgx, fgy. In each of these cases, there's a common function. So this function is effectively multiplying both of them, and we can write this as fx, fy. G will be out front. This function f is multiplying both of them, so we can now write this as f into gx, gy. And at the end of the day, this is going to give us gradient of f times this function g, f times the gradient of g, which is the same thing as saying the derivative of f times g plus f times the derivative of g. Now note, whenever we have a product of two scalar functions, this is a scalar, but when we find the derivative, this has to be a vector. Now at the same time, this is a vector, so the result is indeed a vector as we expect. There is a quotient rule. I will just state the result that the derivative of a quotient will be the derivative of the top times the bottom, subtract the top times the derivative of the bottom, all over the bottom function squared, provided that this bottom function doesn't equal 0 at that point. Is there a chain rule for multivariable functions? The chain rule is the differentiation rule for composite functions. So if I have a function that depends on some other function, the t will be our independent variable, and this thing g will be our dependent variable. we would like to find the derivative of this function y with respect to the independent variable. The chain rule says I have to differentiate the outside layer f with respect to that dependent variable g, then multiply it by the derivative of that dependent variable with respect to our variable t. Is this going to be the case for a multivariable function? We are going to start with the case where we've got a function of two variables, but each one of those variables depends on a single variable t. So in this particular situation, we are going to say that t is the independent variable and that these x's and y's are going to be what we call dependent variables. So we are going to say that x of t and y of t are differentiable functions defined on some set t. This set t lives on the real line. So if we have the real line here, t is just going to be some interval that is contained on that line. If these functions are differentiable, that means x prime of t exists and y prime of t exist for all points in that set t. So we're going to say that D is a set in R2 that contains all outputs of x of t and y of t, but we're going to put them into this vector form, and we'll just call this vector x for now. Once we take all of these points here in t, they get mapped to some new set, and the function that does that mapping is this vector x. We are going to let the function f take inputs from R2 and return a single real number, and we're going to define it like this. Z will be a function of x and y, and we're going to say that this is a differentiable function. So that means the partial derivatives fx and fy exist on every point in D, with fx and fy are continuous functions on D. We take a real number from this set T, we map it to this set D, and then from that set D, we're just going to put it back onto the real line according to this function f. We are going to consider this function z being a function of x of t and a function y of t. What we want to find is the derivative at some point t naught, where t naught lives in that set t. So what we then need to do is talk about single variable derivative, because all we've got is a function of one variable. So as always, we will take our limit definition. We'll have z of t minus z of t naught over t minus t naught. We will have f of x of t, y of t, subtract f of x of t naught, y of t naught, all over t minus t naught. Now you're going to start to see that this notation gets a little cumbersome, and we're going to say that x stands for x of t, y stands for y of t, x naught will stand for x of t naught, y naught will stand for y of t naught. It's going to make it a little easier to write down and read, so we'll have the limit as t goes to t naught, f of x y, subtract f of x naught y naught over t minus t naught. And in order to make some progress, we're now going to do a standard trick. What we're going to do is add in a 0. Now, the 0 isn't just going to be the symbol 0. We're going to add a clever form of 0. So we will put in an f of x naught y with a negative and with a positive. You can see that this right here is just 0. Then we will have the original term there from before, f of x naught y naught. And this is going to give me more pieces to play with. So when I do this, I will now have two terms. F of xy, subtract f of x naught y, all over t minus t naught, plus f of x naught y, subtract f of x naught y naught, all over t minus t naught. These aren't the definition of the derivative yet. I've got some massaging to do in order to get to where I need to go. Now, since f is differentiable, f of x, f of y partial derivative exist, and that means then that the mean value theorem can apply to each variable x and y in our function f. So what I mean by that is If we wanted to, we could apply the mean value theorem, f of x and y subtract f of x naught and y over x minus x naught. So this is just the x derivative of that function at some c and y. Now c is a number between x naught and x. All of these points are just points within our domain D. The term that I see in the derivative expression in the numerator of the first one now can be rewritten in terms of a partial derivative. Similarly, the term in the second numerator can be written like this. I'll have an f of an x naught y subtract x naught y naught all over y minus y naught. I can write this in terms of a partial derivative with respect to y at some point D. Now D lives between y naught and y, and as always, all of these points live in the domain of definition. So the expression that I see in my derivative is the numerator of this fraction on the left-hand side, and it allows me to write it in terms of a partial derivative. And so the derivative of my function at the point t naught is now in terms of a limit. And I've got these two terms. I'll have a partial derivative with respect to x at some c and y, x minus x naught. The whole expression was divided by t minus t naught. And similarly, I'll have fy at some x naught and d, y minus y naught, and the whole expression was divided by t minus t naught. Can I apply the limit laws? Now, in order for me to apply the limit laws, I need to understand whether or not these limits exist. There are four main terms here that I'm going to talk about. I'm going to talk about this expression and this expression first. Since we were assuming that x and y are differentiable on t, x prime of t naught, y prime of t naught exist. That means that the limit as t approaches t naught of x minus x naught, t minus t naught. This exists because it's essentially the limit x of t minus x of t naught. Remember our shorthand notation, and that just equals x prime of t naught. The same thing will be true for the y term. Now, the other terms are a little more involved because they involve these partial derivatives. Now, we also assumed fx and fy were continuous functions. And if they're continuous functions, we have to keep in mind what this limit is asking us for. So for example, if we were to talk about the limit as t approaches t naught of this x partial derivative c and y, we are talking about a limit as t goes to t naught, the partial derivative of this function at some c point, that's a function of t, y of t. Because it's a continuous function, this limit must exist, and this c of t is going to approach our x of t naught, and this y of t is going to approach our y of t naught. We know that these limits exist because the y and the x are differentiable. That means they have to be continuous. This limit is going to end up giving me x partial derivative at x naught and y naught, which is essentially the same as saying f of x at t naught, y of t naught. The derivative of this function at t naught, if we apply the limit laws, all of the limits exist. So what ends up happening here at the end of the day is that we will get the partial derivative of this function at the point x naught, y naught, times x prime at t naught plus the partial derivative of this function at y at x naught, y naught times y prime at t naught. So another way to write this would be partial derivative with respect to x at x of t naught, y of t naught times x prime of t naught plus the partial derivative with respect to y, x of t naught, y of t naught times y prime of t naught. Now another way to write this would be partial z partial x times dx dt plus partial z partial y dy dt. Remember that z was a function of these two variables. Now remember that this is the special case of the chain rule when we had two dependent variables but only one independent variable. Now, another way to think about this special chain rule result is in terms of our d or gradient notation. dz dt you can think of as a vector that has dz dx, dz dy dotted with x prime of t, y prime of t. The derivative of the function z dotted with the derivative of some vector function x here, df dotted with dx. So this looks almost identical to the chain rule from before. And that's a nice reassuring result. All of this material generalizes quite nicely. So as an example, let's find the derivative dz dt if our function z is the natural log of x plus 2y, and x is now sine of t, and y is cosine of t. The derivative dz dt, there's only one independent variable, and that's a t, but there are two dependent variables. So we need to take a partial derivative with respect to x, and then dx dt, plus a partial derivative with respect to y, dy dt. dz dx is simply the x partial derivative of this expression, natural log of x plus 2y. That's 1 over x plus 2y times the x partial derivative of x plus 2y. So this is going to be 1 over x plus 2y. The partial derivative with respect to y is going to be the y partial derivative of this expression, natural log of x plus 2y, which is going to give me a 1 over x plus 2y partial derivative of x plus 2y like this. So this is going to give me a 2 over x plus 2y. dx dt is simply just negative cosine of t. Remember that x of t was sine. And dy dt is just going to be sine of t because x was cosine of t. The derivative here is going to be 1 over x plus 2y times negative cos t plus 2 over x plus 2y times sine t. Everything here is written in terms of three letters, x, y, and t. But remember, there's only one independent variable. So everything here needs to be written in terms of t. X was sine, so we'll have sine of t plus 2 cosine of t times negative cos t plus 2 over sine t plus 2 cos t times sine t. Now, in addition, if I wanted to say evaluate the derivative at 0, everywhere I see a t, I'm going to plug in a 0. So I'll have the sine of 0 plus 2 times the cosine of 0 times negative cos 0 plus 2 sine 0 plus 2 cos 0 sine of 0. I know that the sine of 0 is 0, so this entire thing is 0. This is just going to end up giving me a negative 1/2. I can also generalize this result. So if I have a function of many dependent variables and each one of them is just a function of a single independent variable t, if I wanted to take the derivative, all then I need to do is apply partial derivatives with respect to each individual dependent variable times the appropriate ordinary derivative. So if I go through and I write it out like this, you can see that the results generalize quite straightforwardly and nicely.